In this video, we're going to talk about the shortcuts of finding normal distribution and inverse normal distribution in the calculator. So first off, if you haven't done the warm-up, it is on the screen. Go ahead and pause the video, get this down, make sure you're getting the warm-up. So starting off, we have normal distribution. So that's when we're given boundaries and we want the area underneath the curve. So the question will either say area, percent, probability, fraction, things like that. So the first thing we need to do is go to second bars, go down one time because we want to use normal CDF, and press enter. We then need to fill in our information. It'll ask for the lower bound, upper bound, mean, and standard deviation. And while we work through examples, we'll talk about what those lower and upper bounds are. Once you fill in all your information, go down to paste and press enter 2 times. So on these examples, we did these the other day, but using z-scores and that z-score table. This is just us using the calculator instead to show that we can also get the same thing. So the first thing is putting our diagram together. So we have the mean in the middle at 291.75, and then our boundary for part A is 277. So the question is, why did we shade to the right of 277? And the reason is it says the drives travel at least. So at least means 277 or more. So that's why we shaded to the right. So writing down our information before we put in the calculator, we have lower, upper, mean, and standard deviation. So in the question, it says the mean is 291.75 and the standard deviation is 9.4. So now looking at the picture, to determine our lower and upper for any normal distribution curve, we look at where our shading starts and where it ends. So if we look, we can see our shading starts at 277. So that is our lower. Now the question becomes, okay, where does that shading end? It goes to the end of the right tail. And so for normal distribution curves, our tails represent infinity. So the left tail is negative infinity and the right tail is infinity. Our calculator does not have an infinity button, so instead for negative infinity, we write negative 1e99 in the calculator, and for positive infinity, we write 1e99. So then the question becomes, how do we get e in the calculator? And you press second and then the comma button. The comma button is the button above 7 on the calculator. So our upper here will be 1e99. We go to the positive right tail, so that is positive infinity. So in our calculator, we're going to press second bars, go down one time and press enter. And then you have to put your information in order. It won't let you skip around. So first thing we're going to put in is the lower at 277, then the upper, so 1, and then to get e, again, we're going to press second and then comma, and after we do that, we press 99. We then put in our mean of 291.75 and our standard deviation of 9.4. Go down to paste, press enter 2 times, and we get the percent of 0.94, so 94.2%. So then part B, we want to start the same way, draw in our diagram with our shading. So it says we're traveling between 293 and 313 yards. So we're shading between 293 and 13. So identifying our different parts of our normal distribution. Again, our mean and standard deviation haven't changed. So the mean is 291.75 and the standard deviation is 9.4. If we look at our shading starts at 293. Our shading ends at 313. So if you have 2 boundaries, our shading does not go to either tail, so we're not going to use negative infinity or positive. Our lower is 293, our upper is 313. So then using the same calculator steps, we put our information in to find our percent, and we get 0.435 or 43.5%. So next we have inverse normal distribution. So inverse normal distribution, that's when we're given the area underneath the curve and we want to find that boundary that makes that area possible. So the first thing is press second bars. This time we need to go down 2 times to inverse norm and then press enter. Just like with normal CDF, we then need to fill in our info. That will be the area, the mean, and the standard deviation. Now, with the area, if you have a calculator like the ones we have in the classroom, you can do the area to the left or the right of the boundary. However, if you have an older model, it only calculates the area to the left. If you are going to use a school calculator for the AP exam, it will be one of those older models, so I will always be modeling area to the left. But do know, if you have a personal calculator like the classroom calculators, you can change your tail to the right. Once we fill in that info, we're going to go down to paste and press enter 2 times. So here's our first example. We're talking about SAT scores. It says the mean is 500 and the standard deviation is 100. A college will only admit the top 10%. So we want to figure out what score is that boundary cutoff. So top 10, that is the top right tail. So the 0.01 represents 10%, and again, right tail. X is that boundary of the cutoff score to have to be in the top 10% of those scores. Now remember, if you have a calculator like the ones we have in the classroom, you can use that right tail. But if you have a different calculator, it always has to be the area to the left of our boundary. So I will be modeling that. So the next thing we need to do is find that area to the left. And so that will be 1 minus the area to the right, which is 0.1. So our area to the left is 0.9. That's what I'll be using to put in the calculator. Again, if you have a calculator like the ones in our classroom, you can do right tail and put 0.1 in instead and should get the exact same answer. So with inverse norm, again, we're using inverse because it gives us the area underneath the curve. It asks for the area, the mean, and the standard deviation. So our area, again, using the area to the left is 0.9. The mean, it told us, was 500 with a standard deviation of 100. So putting that in, we get the boundary of 628. So that means students need to score at least a 628 to be in the top 10% of the people taking the SAT. So part B of this example says if there are 5,000 students applying for admittance, how many do we expect to be admitted to this college? Here's the thing, we don't need to use normal CDF or inverse norm. We have 5,000 students. We know they take the top 10%. So we just need to find 10% of 5,000. So 5,000 times 0.01 would be 500. So we expect 500 students to get into this college. Our next example. So this example is all about cereal. So a cereal manufacturer labels boxes as 16 ounces, but the average is actually 6.3 with a standard deviation of 0.2. They want to figure out the fraction of boxes that are underweight. So we are considered underweight if the weight is less than 16 ounces because that is what they are marketing the cereal as. So less than 16, we are shading to the left side of 16. So this is going to be a normal CDF because we want that area, percentage, fraction. Those all mean the space underneath the curve. So if you notice, our tail goes to the left, so that is negative infinity. So we put in negative 1E99. Our upper, we stop at 16. The mean in this question is 16.3, and our standard deviation is 0.2. So when we put those in, normal CDF, go down to paste and press enter 2 times, we get the percent of boxes that are underweight is 0.0668 or 6.68%. Now here's the thing, continuing with this example, the company's lawyers say that 6.7%, aka our 6.68% is too high, and we shouldn't have more than 4% of boxes to be underweight. So we need to reset the mean. So that's what we need to figure out. So that middle line, the mean, is our unknown. We're still advertising that the cereal is 16 ounces, but the percent to the left of it can be no more than 4%, so 0.04. It didn't say anything about changing the standard deviation, so our standard deviation stays at 0.2. So the question becomes, how do we find that mean? We have the area underneath the curve. So if we try to do inverse norm, it asks for the area, the mean, and the standard deviation. We don't have that mean, so we can't use inverse normal distribution. So instead, what we're going to do is we're going to go to our z-scores. We're going to find the z-score using our standardization of scores, and then from there we can find the mean using the z-score formula. So using our standardization, we find the z-score by using the area given, and then our mean and standard deviation, don't forget, it will be 0 for the mean and 1 for the standard deviation. So anytime we have the area underneath the curve, we can always find our corresponding z-score using 0 for the mean and 1 for the standard deviation. So putting that in, we have the area to the left, so we don't need to change it. It's 0.04, mean is 0, standard deviation is 1, and we get a z-score of negative 1.75. So now that we have our z-score, we can put it into the formula, and that is x subscript I minus the mean over standard deviation equals z. X subscript I, that is our given data value, aka our boundary, which is 16. The mean is what we want to find. Our standard deviation is 0.2. So multiply the 0.2 over to the negative 1.75. And so we'll have negative 1.75 times 0.2 equals 16 minus the mean. So move everything over, get the mean by itself. We get the mean is 16 plus 1.75 times 0.2. So our new mean needs to be 16.35. So normal probability plot, we didn't talk about this in the other classes, but it's just if the distribution is roughly normal, the plot should be a diagonal straight line. And so essentially your points are the data value, comma, the z-score. So you need to find the z-scores for each of them. The book mentions it, but then we don't really do anything with it. We didn't take down the exit question, but here is your homework associated with this lesson.